So, good morning. So in the last class, we have anything by using controller. Then what would be doing is we are going to interface. Like now, let us take you have sensor. So now, if you have any sensor, now let us take an example of monitoring the room temperature. So the temperature, if it is of room temperature, you have to monitor and then display. So now what you need to do here is you need to interface that particular sensor, sensor, and then now you have to display. So now let us take this example. So the example is now what you need to do, you need to interface a sensor to the microcontroller, and then you read the temperature of the particular environment, and then you display it on LCD. So here what we need to do, we need to interface this LCD. Now let us take the display which you are going to take is an LCD, and LCD now need to be interfaced to the microcontroller, and the sensor, the output of the sensor is analog. Okay, so the output of the sensor is an analog. Now let us take, you can take thermistor or thermocouple, any kind of sensor you can take. So now let us take the output of the sensor is analog in form. Now that has to be converted to the digital. So there is no onboard analog to digital converter on 8051. So this is what the 8051 Intel based microcontroller is, what we are dealing. So now it has no onboard ADC, it has onboard RAM, it has onboard ROM, it has onboard ports, it has onboard timers. So timers we didn't discuss, but I'll try to discuss this in the next class, the timers and interrupts. Okay, so it has onboard ports. So now the ports of 8051, now directly you can connect it to the sensor, but the sensor output is analog signal. So this analog signal now need to be converted into digital. For that we need A to D converter is. So we need A to D converter. So, but there is no onboard A to D converter. So then what we are going to do is, we are going to use an A to D converter. Now let us take 0809 IC. So 0809 is 8-bit analog to digital converter. So now the sensor output we are going to A to D converter, which is 0809 IC, and that output we are going to give it to the 8051 microcontrollers. So now, and now we need to display that on a LCD which is of 2x16 or 2x20. The commercially available LCDs are 2x16 or 2x20. Means 2 rows and then 20 columns you can display. Right. So now the task is, you need to interface, how to interface LCD to the microcontroller, how to interface analog to digital converter to the microcontroller, and then that is what we are going to see in this particular class. So the first part I will be taking care of, how to interface A to D converter to microcontroller. So A to D converter to the microcontroller. So how we did in microprocessor, through 8255, connecting external 8255 and then 8089 and then the sensor. So here the advantage of the microcontroller is you have an onboard A to D converter. So you have onboard A to D converter, so that we can use onboard port. You have onboard analog port. So we are going to interface analog to digital converter. So that is what the first interface I will try to take. And the second interface which I am trying to take is interfacing of LCD. So this I didn't cover in microprocessor part. So interfacing of LCD, and then the next one is how to interface digital to analog converter. So how to interface digital to analog converter is what we'll try to see, and how to interface, right? How to interface now keyboard. How to interface keyboard, right, to 8051 is what we'll try to see in these particular classes. So that's what we are going to see, microcontroller interfacing. So in microcontroller interfacing, what we do is, so how to interface analog to digital converter to LCD, and how to interface how to convert interface A to D converter to 8051, how to interface LCD to 8051, how to interface digital to analog converter to 8051, so that we can make a system, is what we will try to see in these particular classes. So is that all right? So that is what the agenda for today's class. So after completion of this class, you should be able to learn how to interface A to D converter to 8051, especially 8051. If you take some other microcontrollers like PIC microcontroller, Atmel microcontroller, this A to D converter is on board available. So that means, you know, A to D converter is also on board, on chip it is. So that feature is not there with 8051. So then what we need to do, we need to interface sensor to 8051 microcontroller. So that part is what we are going to try to take in these particular classes. Right, so now coming to the analog to digital interface converter, and we have seen the hardware, complete hardware of analog to digital converter. So now if you try to see the hardware, it is a 28 pin IC, and this 28 pin IC, as we said, there is, you know, how many analog inputs you can connect. So you can connect 8 analog inputs, so IN0 to IN7. So 8 analog inputs you can connect at a time, but only one input can be digitized. So selection of that can be done by using select lines. So in 8086, I clearly explained like how to, you know, what is the algorithm we need to follow. So here we are going to see this again, because the analog to digital converter now need to be interfaced. So now if you try to take, you know, this analog, and then this is what, you know, the like, you know, if you these are the multiplexer. So it is an 8x1 multiplexer, so 8 inputs, 1 output. So any one of the 8 inputs can be selected by using ADA, ADB, ADC. So if it is 0 0 0, if A is 0, B is 0, C is 0, then channel 0 is considered. And if it is 1, and if it is 0, and if it is 0, then channel 1 is considered, channel 0 and channel 1. And then if it is 0, and if it is 1, and if it is 0, right, if it is 0 and 1 and 0, so then at that case the second channel is going to be considered. So like that you have, so the first step is you have to know where, so which pin your analog input is connected. So that is the first step. The second step is selection of that can be done by using the select lines ABC. So which signal need to be sent on that has to be seen. That is second step. Then the third step is these signals has to be entered into analog ADC IC. So then what you need to do is you have to give a ALE pulse here. So once you give the ALE pulse, then the data which is available on this ABC, that will be getting into the multiplexer, so that that particular channel is getting selected. So that is, you know, so the step number 1 and step number 2 and step number 3, giving ADC pulse. So then the channel is getting connected to the input of the analog to digital converter. So then the step number 4, what you need to do is you have to give, now you have to tell the ADC that you start conversion. so that you have to give a pulse on start pulse, the start pin. So then it starts converting, and based on the clock speed, it takes, if it is in a 8-bit converter, it takes 8 clock cycle, because the analog to digital converter which we are seeing is an 8 cross 1 multiplexer. Sorry, 8-bit analog to digital converter. So 8-bit analog to digital converter means it takes 8 clock cycles to finish. It is a successive approximation type analog to digital converter. So when it is successful, then it will be taking 8 clocks, and then the speed of conversion depends upon this. So you need to wait, the processor, the controller need to wait up to 8 clock cycle. So then once the processors, once the analog to digital converter starts the conversion, then it indicates that by the end of conversion, that this particular pin, if you try to see, it is getting low. Once the conversion is done, then this particular end of conversion is becoming high. That means what? The conversion is finished. So you will be keep on in step number 5. What you need to do is you need to check the end of conversion signal. If it is low, then the analog to digital converter is performing still, it is converting the analog bits into digital bits, and otherwise you have to wait. So then once the end of conversion is done, if it is high, then the conversion is finished. So then once the conversion is done, then the bits are available on analog to digital converter. Now you have to bring these digitized bits onto the microcontroller. So then what you need to do is, in step number 6, what we need to do, you need to give output enable signal, so that the data which is available with A to D converter, it comes on to the data bus of it comes on to the data bus of the microcontroller. So that is the step number 6. So that with that it ends. So now let us try to write the algorithm. Okay, for this, and the same algorithm now we need to see as in a program. Okay, so now let us try to see algorithm part. Okay, so this is what we are going to use, the successive approximation type. So this is the analog to digital converter which we are talking about, the internal block diagram. The hardware, here you have 8-channel multiplexer, which has 8 analog inputs, and any one of the 8 analog inputs can be selected. Any one particular analog input can be selected by giving this 3-bit address and giving an address latch enable, and so that any one of the channel is getting selected. So this is successive approximation type resistor. So the conversion, the conversion can be started. The conversion can be started by. So the conversion can be started by giving one start pulse here, and then you need to wait for end of conversion. So where is the end of conversion here? So end of conversion signal is what you need to check, and yeah, here this is what your end of conversion. So if end of conversion, if it is low, then the converter is converting that, because it needs 8 clock cycles. And if it is now, if you assume the clock period here, if the clock period here, if you take example 100 kilohertz. 100 kilohertz is what if you try to take. So then 1 by 100. So 1 by 100 0.001 0.001 millisecond. So that means that is around you can take it as 1 microsecond. So 1 microsecond is the conversion period. So it requires 8 microseconds. 8 microseconds. So each clock of the microcontroller is of one clock period of the microcontroller, if it is working with 10 megahertz, then each one will be 0.1 microsecond. So it has to wait 8 microseconds then. So then that can be indicated by using this particular end of conversion signal, right? And once the conversion is done, that is available in this tri-state output latch buffer. So then what you need to do is you have to give output enable signal. So here output enable pulse, then they are available on the this is the here if you try to see that they are available on these 8 bits. This is what your LSB and MSB, so 8 bits the outputs are available. So this is what the hardware we are going to interface to the microcontroller is. So here now if you try to see, so step number 1, so screen, if you need to see, yeah, now, so now step number 1, now, so now the algorithm if you try to write, so connection is what we have seen. Now here so ABC, if it is 000, so you can select this particular channel, and now this is what the steps you need to follow. Select the analog channel by providing bits on ABC, that is step number 1. So this is step number 1. This already we discussed in 8086, when we interface this is 0809 with 8086 microcontrollers. Okay, right. Then the second step is activate ALE pin. So step number 1 is this. Step number 2 is you have to give a pulse on ALE, then activate startup conversion signal. So you have to give startup conversion signal a low to high pulse on initiate conversion, and then you need to monitor end of conversion. So if the end of conversion, if it is low, right, then that means up to 8 microseconds is what the processor has to wait. But and then the next one is you activate the output enable. So these are the steps 1, 2, 3, 4, 5 steps need to be followed. And now let us try to see. Let us try to connect your this flash type or SAR, successive approximation type converter to the microcontroller, or this can be of 8051. Okay, this can be of 8051. Now how many pins will be requiring? So how many pins will be requiring to connect this? So connect this to microcontrollers. Now we know the hardware of analog to digital converter. So we know the hardware of analog to digital converter, and now let us try to see how they are. So now yes, the digitized bits can be read by port 1. So port 1 8 bits. So this is 8 bit. So this is 8 bit. So this is 8 bit analog to digital converter. 8 bit analog to digital converter, and the analog bits we are giving here, right? And yeah, there should be an example of this is flash type AD converter is what it is given, but we can make it no problem. So here this IC, if you try to see, it has chip select pin. So now ALE, startup conversion, end of conversion, VCC and ground. Okay, so here this is what the example from Ayala I have taken. So you can convert connect SAR IC or this one. So now here the chip select means analog to digital converter has the chip select. If this pin is going low, so this pin if it is going low, then this IC is getting selected. And then next one is write and read. So write and read means you can consider this as yeah, writing this into start of conversion, and this you can take it as end of conversion. So you can take it as EOC. So end of conversion is what you need to read, because conversion is done or not is what you have to see. So that is connected to P3.4. So port 3, fourth pin is used to connect end of conversion. P3.3 is connected to start of conversion, and here you have output enabled to, you have to give a pulse, right? So that pulse, and then you have here, so this is similar kind you can make. So I can use another three port signals of port 3 to connect it to ABC. Okay, ABC. So the ABC is of the this is flash type A to D converter, which is much faster than SAR, and you can choose either flash type SAR or flash type A to D converter, or you can choose successive approximation by A to D converter too. So if it is flash type, either you can do that also. Then what you need to do, you need another 3 pins here to be connected to flash type A to D converter. Sorry, successive approximation resistor type A to D converter. So 3 more ports is what you need. Right. So if it is flash type, you have write bar, read bar, and chip select. So then all the digital bits are connected to port 1. So now the same thing you need to see in the program. So this is what you can write in your Keel software or somewhere, and then you can try some simulating this. So here, if you try to see the program, the same steps what we have seen now, this should be, we have to find it as in program. So now here this is 8031. So that's why it is not having an internal ROM. So external ROM is connected. So that's why that is pointed out using. So origin means start with 000. So now we have a ROM of 4K. Your program can be originating from 4000. Right. And then now move DPTR to the beginning. Okay. Data pointer will be showing to the begin, and then the begin is what at 4000. That means your program you are writing at 4000, because 4K, if you try to take 40002 03FF 4K or 64K if you have 64K, if you have 4 zeros to 4K RAM. So that means here it is 40 means it is of 64K ROM is externally connected. That's the meaning is that. So your program starts from 400. So then move data pointer to there, right? And now the first step what you need to do is now you can try to take this hardware as a flash type to be converter or SAR. So but this is related to SAR, so which you have chip select pin, which you have write bar, and if you have read bar pin. So now the first step is what, this A to D converter now need to be selected. So that means what, this should be 0. So that means chip select should be 0. So then what you are doing is clear P3.2. So clear P3.2. So clear P3.2 means here P3.2 is what, chip select. When it is made 0, so clear means what, this will be made 0. When this is made 0, this pin is of chip select. So when it is selecting chip select, then that IC is selected now. That is the first step. That is what, clear P3.2. Now clear P3.3 and set the P3.3. So P3, that means what, clear P3.3 and set B P3.3 means here you are giving a low to high pulse. You are clearing it in the beginning and then you are making it high. That means what? A low to high pulse you are giving on P3.3. So what is P3.3? So here P3.3 is writing which is like giving like startup conversion signal. So you are so because it is flash type, if it is successive approximation type 0809 kind of thing, then what you need to do, you need to give 0, 0, 1 or 0, 0, 0 based on where your this input is connected. So input is connected, right? So that piece of program has to be written because this is flash type, that is not there. So now clear P3.3 and set B P3.3. That means here you are giving a low to high pulse, right? Then startup conversion is given. So then after that, what you are doing is clear P3.4. So clear P3.4 means by default it will become end of conversion low. So you are giving here P3.4 low. So 0 you are giving. Right, 0 you are giving P3.4 and now move P1 comma A. So P1 comma A. P1 is what? Port 1. So P1 is what? Port 1. So that means when the end of conversion is becoming low, then what happens? The digital bits are available here, so those digital bits has to be brought into the microcontroller data bus. So that can be done by using this. So now set the P3.4. So now you are moving that into accumulator. All right. So now you cleared P3.4 and set the P3.4. Okay, so P3.4 is your end of conversion. So once it is getting high, then what you are doing is whatever is there in accumulator, you are moving to the data pointer. So the data pointer is as at beginning at 4000 is what you are going to say. So this program is this program somewhere it has to be there. Interface a flash type A/D converter to 8051 microcontroller and then store the digitized bits at 4000. So your program is starting at 0000 memory in 64K. So now if you can consider the 64K like this, so 64K ROM, this is 8031, that's why it is there outside, but you can save this in on chip ROM too. Okay, right. So now here is your 0000. So your program code, this code equivalent bytes, this code equivalent machine level language program is going to store from 4000. You write a program to interface a flash type A/D converter to 8031 microcontroller, and the digital bits like around monitor the analog to digital converter bits for around 10 milliseconds, and then the 10 millisecond or 1 second, and you save the data from 4000 you save the digitized data for 1 second or 2 seconds. So the data which is available is what you can save at a particular memory. This is what the requirement. Interface a flash type A/D converter to 8031 microcontroller and then store the digital bits at 4000. So 400 is your data and your program is at 0000. So you are moving that to the, so this is the, we have seen the addressing modes in the last class. So move X is the command to transfer the data to the outside world. But whereas in microprocessor, it was out instruction. That was an out instruction, but here move X instruction. So at where the data pointer is pointing out, there you move the accumulator content, right? So then, right, so this is what you have to do. Now increment the data pointer and then move DPH into accumulator. So it is C compare and jump not equal, then A and wait. So because here this is flash type A/D converter, that end of conversion signal, you have to write the bits clear with 3.4 and set B with 3.4. So that means, here you give a low to high pulse, and that low to high pulse will bring you the data onto the port 1, and that port 1 content you are moving into the accumulator, and that accumulator content you are saving at 4000. Is it all right? And now you will be giving little bit delay. So here the delay, you will be having a delay subroutine written at 74H, and now the time, you are taking a time into delay of delay of 87 microsecond. Right, so that much time you get the digitized data, and then you save that into 4000. So then that you are decrementing, you are comparing the content, okay, and then checking like if it is not 0, so then you keep on doing the same. Right, so this is what a simple program, it can be written. Only the thing is the instruction set. You try to see here, it is clear, bit programmable. 8051 is of bit programmable, is what you can try to see. So this is what your interfacing of 0809, and the same thing you can extend it to interfacing of 8051 with 0809. So then what you need to do, you need same port 1 you can use to read digital data, and here you can give your chip select, and here you can give start of conversion, end of conversion, and you need another 3 pins of the port. So port pins you need, another 3 port pins you need, where you can give end of conversion and end of conversion. So another 1 port you will be needing for ALE, okay, ALE, and another port pin you will be needing for output enable. So if it is successive approximation type analog to digital converter, you will need 5 more pins now need to be connected to 5 more pins need to be connected to the microcontroller. So 5 more port pins of P3 is what you can consider, and then the same algorithm you can write in terms of the program is. So this is what your simple program. Okay, so this data pointer, no need of writing data pointer, or you are somewhere storing in the memory, so that memory can be you are starting at 4000, and then you can go ahead, right? So this is what your simple program of microcontroller is. So now let us try to take interfacing of DAC IC to 8051 microcontroller is. So DAC is digital to analog converter. So microcontroller is in a digital device, and it gives, in terms of, it is an 8-bit microcontroller, so 8 data bits it gives. But we cannot understand that binary bits. So now if it is converted, it has to be converted into analog bits. So what we need to do, we need to interface digital to analog converter to microcontroller, 8051 microcontroller is. So now if you try to see the 0808 IC hardware, right, 0809 IC hardware, this in detail is what I have seen. Okay, this is what we have seen now. So now is it all right? Okay, so now same thing what we have done, we are doing with microcontroller. Okay, is that all right now? So VNRSC college, right? So now is what I am trying to take up in next 20 to 40 minutes. All right. So now let us be ready, be focused, and then let us concentrate. Okay, right. So now let us see. So now this is what the digital. Yeah, now let us take digital to analog converter. So this digital to analog converter IC is this. So now you try to see the pins. You will give 8 digital equivalent bits. So 8 digital equivalent bits from the microcontroller. So now let us take here you have a microcontroller, right? Here you have 8 data pins, digital bits, and 7 and 8. These 8 bits D0 to D0 to D7, D0 to D7, you can connect it to A1, LSB is 8. So here you can connect D0 of the microcontroller, right? This is D1 and so on up to this is your D7. Okay, that is what the connection is. The output is, and the input is analog, digital, output is analog. So that analog is available on this IO pin. And this is how anyhow you will connect it to VCC, and this is anyhow you will connect it to ground, and the reference voltage while it is converting is V reference is what we consider is. So possible I'll try to show you. Yeah. So now this is what the hardware connection is. So D0 to D7 is connected to 765431. So the pins you see 7, 6, 5, 4, 3, 2. Now you see D0, D1, D2, 3, 7, 6, 4, 5, 6, 7, and then 13, 14, 15, 16. 13, 14, 15, 16. 12, 11, 10 and 9 here in this case. Okay, right. So now this D2A converter has to be connected to microcontroller. So microcontroller, so 8 pins are needed. So what I am doing is any external device has to be connected through ports. So I am using port 1 here. All right. Okay. Then the output is I out, analog pin is available. So the output of D2A converter is current. So that has to be converted into voltage. So that voltage can be converted by using a current to voltage converter is a simple operational amplifier using one resistor. So current flows through this particular resistor and that current is converted into voltages. Is that all right? Yes. Then first thing is this chip select, when it is 0, then this IC is getting selected. So we have to make this chip select 0. Very good. Then this IC is connected. So the microcontroller places the bits on the port 1. Okay. Right. And then the converter will convert that into analog output voltage. Okay. So that is available on 11th pin. Right. Okay, so now that you have to see on a CR. So as an example, to give, so this is what the hardware connection is. So you need how many port pins? So here you need 3 plus 8. So 10 port pins to connect your D2A converter. So now to demonstrate this interfacing, so now let us try to use generate a ramp signal, using microcontrollers. So that means, so microcontroller, so when here it is, the microcontroller is giving bits 0, 0, 0, 0, 0, 0, 0 and 0. Okay, then increment that up to FF. FF is the maximum reference voltage. Let us take 5 volts. Then immediately when it is FF, then again you start with 0, 0 kind of thing. So generate a ramp signal using microcontroller is what example we will try to consider. So now let us take the program. This is simple 4-step program. Now move accumulator 0000 and move A into the port 1. So port 1, so your microcontroller data bus D0 to D7 is connected to D2A converter through ports. So port 1. So you are giving all 000 to port 1. So this is done. Then increment accumulator. Okay, increment accumulator. Right. And then here, so earlier it is 000. So then this here you can write this back here. You can write your back here. So you incremented, so you increment the accumulator, so it became 1. Then sjump back. Okay, incremented, right, then you went back. So then the content of A moved into the port 1. So port 1 is connected to the D2A converter, so it will now give 1. So that will be connected into equivalent analog voltage, right, equivalent analog voltage, and then done. So now what you can do, increment A and then move into the port, jump back. Here you can put a counter here. So here what you can do, move B FF. Move BFF. This is what your counter, which is of equivalent of 5 volts. So increment A and then decrement B. Then so here you can use the command decrement DJNZ. Jump no 0, decrement, yeah, so decrement B, and if it is not 0, so then you can go back. Okay, so this is back 1, and see now, very simple. Generate a RAM signal using D2A converter, which is interfaced to the microcontroller. So now what we are doing, move A comma 00, move B comma FF. So B is the counter, is what I am using. Now this 00 is what you are writing at the port. Now you are incrementing A and you are decrementing the B, and if it is not equal to 0, then move the content of A into the port 1. Then again increment A, it will become 002 now, and you are okay, and decrementing B, and if it is not 0, then you are going back, right? And then so like that, it will increment up to F, and then you are going to give it in port 1, which is going to be converted into equivalent voltage by using your D2A converter, right? Okay, so then once it is F, so then what you can do is sjump, short jump, short jump, back 1. So here back 1 is this. So one, it is a decrement, and then if it is not 0, you will send it to port 1, right? Once it is 0, then it will come down. Then what you are doing, you are jumping at to this. Again, you are giving 0, 0, 0. Right. So again, you are giving 0, 0, 0. So then again, you are starting the process. This is what the simple. I think you know how many steps? 1, 2, 3, right, 4, 5, 6 steps program. Generation of the interface, digital to analog converter IC to the microcontroller, and generate a RAM signal on it. And this waveform, if you connect this to CRO, you can view this particular waveform. Is that all right? Yeah, that is the second interfacing. So now let us interface LCD, which is very important. Okay, so this is very important. So now let us try to interface, because this I didn't cover in microcontrollers, 8051 microcontroller when I am dealing. So this I didn't cover. So are you with me? Like up to now what I discussed, this interfacing of LCD interface, is that all right? So is this clear? Yeah. So now this is very important. Like if you are doing, or if you are interfacing, or if you are using an Arduino board, then also LCD you have to mostly that on chip is Atmel. So if for any microcontroller, you have to interface this LCD, and then any interfacing and you have to write program means you should be very clear with the hardware. That's what much sure. You have to know assembly level language program. In the end, the program is of C plus assembly. C plus assembly. So cross compiler you can use. That is the final thing which is used in industry. Right. So I am covering assembly level language program. So be careful. Just pay attention. We are going to now interface LCD to 8051 microcontroller. The moment we say LCD interfacing, what we should know, we know what is the hardware of LCD, right? Okay. Then now let us discuss the hardware of LCD. All right. So now let us see the hardware of LCD. So this is what the LCD fit. So now you see how many data lines are there. You have to be with me. We are going to discuss this in very detail. See, the contrast of the LCD can be done by using a potentiometer at this +5, -5 and ground. I repeat, the contrast of the LCD. So potentiometer means what? Here you have 3 pins, right? So one is connected to +5 and -5 and ground. Okay. So then the moment you are varying this +5 and -5, and then here ground, then you are varying the voltage. The moment you are varying the voltage, the screen will be getting disappeared. So the contrast, you can, I think I have slide, I can show you. I think yes, I can show you. Just a second, I'll have this port pins very clearly. I'll show you how that can be done. Now, no, I made slides, but I forgot to copy here. And now Just a second. LCD interfacing is what now need to be seen. So LCD, where is PPT? Now LCD interfacing. Now just a second, I'll show you the things: motor drive, LCD, proximity sensor. 7 segment. This is 7 segment display. LCD. That is the program, but this is 7 segment display. Somewhere. This side, the LCD interfacing should be here. Yeah, anyhow. So I'm not getting what I did. Long back I did. So here, now if you try to take LCD interfacing, here you have LCD has this pin. So this you will connect it to a potentiometer, so that the potentiometer, when you vary, then the contrast of the LCD is getting varied. And now you try to see the bits D0, D1, D2, D3, D4, D5, D6 and D7. So these bits, you can write into LCD. So now let us consider it is 2x20 LCD, right? 2x20. So you can write into LCD by using these bits: D0, D1, D2, D3, D4, D6, D7. And this is resistor select. RS is resistor select. RW is read or write LCD. And 6 is enable. Enable means you are from this controller to the LCD, you are one IC to another IC. When you are transferring the data, you have to give a pulse. So that pulse is enabled. So how many pins with LCD? D0, D1, D2, D3, D4, D5, D6, D7, 8. Register select. There are 2 resistors with LCD. That is, one is command register, another one is data register. Command register is configuring the LCD. What do you mean by configuring the LCD? I want to display a character in row 1 at column 5 is what I want. So I have to configure that. And another thing is, how many dots per character is what I need. That I have to mention. I'm writing a letter. So how many dots on liquid crystal I have to use? I have to know. So I have to do configuration before writing into the LCD. The configuration can be done by using this RS pin. If RS pin is 0, command register is selected. If it is 1, data register is selected. Now I want to display hello is on this particular LCD. That is what the task we have to do. Interface this LCD to the microcontroller and display hello. This is what the task. Now let us see how it can be done. So first what we have to do is we have to configure LCD. And while you are doing configuration, you have to write in command register. And once you configure it, then you have to choose data register in which you write H, E, L, L, O. So that is what RS pin. And read write. Now let us take, you are writing H. whether that H is correctly written into LCD, whether LCD is busy in writing. So then sometimes you need to read. Okay, so you are going to write into it. That depends on this RW bar button. And whether it is busy, LCD is busy or not, you have to read that through this R and W pin. So whenever you write something into the register, give enable signal. So now let us try to see how you are doing this. So this is 1, 3, 2. This is a variable resistor, and this is how you connect it in contrast. And register select, and then read, write, and enable. So now these are the physical meaning of each bit. If RS is 0, command register is selected. RS is 1, data register is selected. And if RW is 0, then you can write into the registers. And if it is 1, you can read them. E is for enable. And D0 to D7 are 8-bit data bus. Now, coming to the configuration of the LCDs, you have to be very clear. You have to be very clear understanding of this LCD. Once you understand, it will become very simple. So I told you you can use the command register. That means what? You can give 0 here on the register select, and you can select the command register. And you can send these bits into the command register using D0 to D7. Right. So now RS is 0, RW is 0, means you are writing into it. Then if D0 is 1 and all they are 0, means what? Clear LCD and memory home cursor. The cursor will be blinking on LCD, right? So that cursor has to be the home position means, and LCD has memory. That memory has to be cleared, means this is the command you need to give. This is the command you need to give into the command register. Command is 01. But for that, register select should be 0, and this you have to write into command register means RW bar pin you have to give 0. And if D1 is 1, if D1 is 1, clear and home cursor only clear LCD, not the memory and home cursor. And if the bits are this, you want to shift the screen or if you want to shift the cursor. See, once you display, your cursor has to be move to the next position, right? So that depends upon this D0. Now let us take this is 1, then the cursor is moved towards the right. If it is 0, then the cursor can be moved towards left. That means when it is 1, so when it is 1, then the cursor can move towards the right. Otherwise, it is 0, then this bit, if it is 0, then screen will be moved to the left or right. Is that all right? So the screen, if it is 1, shift screen, 0, shift cursor. So if it is, if I want to move the cursor, then I have to give here 0. Okay. If it is 1, then cursor you move towards right or otherwise left. 0 means it is left. Okay, this is what the command. Then next command word is D7 to this thing. B, C, D and 1. When D3 is 1, see here in this case, when D2 is 1, The meaning of this is considered. It can be 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, four possible combination. Moving the cursor or moving the screen, or moving the screen left to right, moving the screen right to left, or moving the cursor right to left or right to left. This is what the meaning. When D3 is 1, okay, when D3 is 1 and when D is 1, cursor 1 means blinking the cursor. You want the cursor to be blinking one or the cursor to be no blinking one. Alright. Okay, so it is blinking or not blinking. B. C is cursor is on or off. You need a cursor on or off. So if it is 1, then cursor is on. If it is 0, the cursor is off. And D, the screen is on or off. The backside screen, it should be on or off. So that is the case when D3 is 1. When D4 is 1, when D4 is 1, when it is 0, 0, RL, shift one space right, or 0 means shift one space left. SC, screen or cursor. You want the screen to be moved or cursor to be moved. Alright. And very important, next one is this. When D5 is 1, all other bits meaning are this. When DL, if it is 1, 8 bits per character. If DL is 0, then 4 bits per character. And D3N. So if it N means 2 rows of the characters or 1 rows of the characters, this N. And then F. 5 into 10 dots per character or 5 into 5 cross 7 dots per character. Is it all right? Okay. I have a slide by which, pictorially I can show you this. I have that, let me I'll show you whatever I am explaining. Yeah. So coming to the LCD interface, yes. This is what the LCD we are talking about. This is what LCD. You see 16 to A means 16, 2 cross 16. Now you see each pin VCC, RS, RW, that will be backside printed on the LCD. The bits are these things. So this is what your LCD. So I told you to connect one potentiometer here. When we are wearing the potentiometer, the screen, getting, see, the contrast you can change like this, when you vary the potentiometer. Okay. Now, 80 is, starting the cursor, the meaning of this, this is what we is seeing. So 0, 1 is the command, you have to write it to the command register, clear display screen. And 0, 2 is the return home, 4 is shift cursor to the left, 6 is shift cursor to the right. Okay. And shift display right or the shift display left. 0, 8 is for shift display off or cursor off. So display cursor off. A is the command we have to write to display off and cursor on. C is the command display on, cursor off. And display on, cursor blinking, display on. So E is the command. and F is the command display on cursor blinking. Okay, and shift cursor to the left, shift cursor to the right. So these are the commands. And if you want to write your character in the beginning of the first line, 80 is the address. C0 means second line, and 38 means 2 lines you are going to write, and 5 cross 1 is the matrix. So this is what, yeah, so this is what you are going to should know. So now let us try to take how it is connected or interface to the microcontroller. So this is what your microcontroller. D0 to D7 are connected to port 1, and register selected is connected to port 3.2, and read write is connected to P3.3. Okay, enable is connected to P3.4. You have to be very clear, and you should be with me. Right, so now let us try to state how to display on the LCD. Hello is what I want to display on the LCD. So the first step what I do is I make this register select 0 by clearing P3.2. The moment it is made 0, command register is selected. Then I make this read write 0 so that I can write into the command register. And the excellent equivalent hexa code is what I have just shown you. I want how many dots per character, I want to move cursor left or right, all these things. That equivalent thing is written into the command register. Okay, and the moment you write, you have to give a pulse. So now let us see the program. Now clear P3.2. So clear P3.2 means what? I am making the register select 0. I am making this register select 0. And clear P3.3. So clear P3.3 means what? I am selecting, I am writing into the command register. Okay. Then move A comma 3F. Move the accumulator 3F. So this 3F stands for 8 bits per character I want, and 2 rows I want to display, and each character is of 5 cross 10. 3F 0 0 1 1 1 1 1 1. Right, 1. So this is D0, D1, D2, D3, D4, D5. So when D5 is 1, so here see, when D5 is 1, and here also 1. So 1 means what? 8 bits per character. So we are writing this as 1. And N also we are writing 1. That means we are going to use 2 rows. 0 means 1 row. And this we are writing 1. F means I want 5 cross 10 dots per character. Okay. So I am writing 1. Right. So then here these are 0 0 or 1 1, and it doesn't care. Right. So this is what I am trying to write in the beginning. So A move 3F, which means 8 bits per character, 2 rows, and 5 cross 10 dots per character. And now this thing now need to be written into the command register. So for writing something, I am writing as subroutine at strobe. What is that strobe now? Let us see. So a call, right? So call the strobe subroutine. So here strobe. Now in strobe, what is there? Now you are going to make port 1 0 FFFF. means configure port 1 as input. See here, see the hardware very clearly. Port 1 is connected here. I want to write something into the command register, but before that I have to see the LCD is busy or not. Means LCD is busy means when D7 is 1, right, when D7 is 1, then it is busy, otherwise it is not busy. So that means I have to read the data bus, and the data bus, if it is 1, I cannot write anything into the LCD. So the first thing what I need to do, I need to see this D7 bit is 1 or not. So it has 1 or not means what I need to do, I have to configure this port 1 as input port. So when I discuss the ports and then the programming, so whenever we want to use the port as input port, then we have to write FF into it. FF means what? 1 1 1 1 1 1 1 1. That means what? When it is 1 1 1, then that will be high impedance state. Then when it is in high impedance state, the buffer is going to be connected to the microcontroller, right? So then set the P3.3, set P3.3. So P3.3 is what? So now I want to read. So the moment I want to read, I have to make this 1. See, I have to write it, but before writing, I am checking LCD is busy or not. So LCD is busy or not. So that means I have to go for read operation. So the read operation can be made by writing 1 1 1 1 1 into the port 1. Okay, that's what we did. And now if I want to read, then I have to make this 1. So that is what I am trying to do. So set B P3.3 and set B P3.4 and clear P3.4. So P3.4 is what? Enable. So then for giving enable, I have to give a high to low pulse. I want to read this into the data bus of the microcontroller. So I have to give a high to low pulse. So high to low pulse can be given by setting P3.4. So setting and then clearing. That means giving high to low pulse. And jump below P1.7. So P1.7 is what? P1.7 is D7. So this D7, if it is 1, means it is busy, you cannot write. So then now you are checking jump below P1.7. That means below means what? They are, if it is 1 means that is busy. If it is busy, then you wait. So then if not busy, that means if it is 0, it is not below. Not below means if it is, if D0 is 0, then what you need to do, set the P3.4 and clear P3.4. So then again, P3.4 enable signal you are giving, and set the P3.2. Set the P3.2 means what? So P3.2 is this one, register select. So now this command which is there, 3F now need to be written. So that 3F need to be written means what we are going to do. So we are going to make now, right. So command register is what we are going to write. So then we are going to make this into a high to low pulse, and this data bus is selected, and move A1 comma P1. So A1 comma P1. A1 what is there? A1 here is having 3F. So that 3F now written into the data register. So the data register is what is now it is getting written. Right. So but set B 3.2. So choose the data RAM and move A comma P1. So now clear P3.4 and set B P3.4. So that means you are giving a low to high pulse but writing this into. So that means here you just take care. If you want to read This thing you have to give low to high to low pulse, and if you are writing from microcontroller into LCD, then you give low to high pulse. I repeat, if you are reading LCD, give low to high pulse so that bits will come into the data bus. And if you are writing from microcontroller to LCD, then give low to high pulse on the enable. So that is what it is done. So now clear P3.4, set B P3.4, right, and clear P3.2. So clear P3.2 means again command register is selected, okay, and then you can go ahead and then return and then end. So when it is ending, it will come here. So then you send 0E. So 0E is what? Command screen, cursor on, no blink. So this 0E has to be written. So then A call strobe. Again strobe, what you are doing? You are configuring this as input port. You are checking that D7 bit. If it is not done, then you are writing that particular content into the port 1. Is that all right? So writing means again you have to give low to high pulse. You are giving low to high pulse, and when you are reading, you are giving high to low pulse. So this is written in the form of subroutine. So every time when you are writing, you can call. So similarly, you can write 06, which is equivalent of command cursor, and 01, clear all and home cursor. Right. These are the commands you are writing into the command register in the beginning. And then now I have to write hello. So move set B P3.2 is selecting off the data register, and move H equivalent is the ASCII character you can take and move into the accumulator. A call strobe. You can use the same subroutine now, writing this into the data RAM of the LCD. Is this clear? And then you can write H E L L O, and then you can use this particular subroutine all the way. Is it all right? Okay. So now you can take this particular example. In Arduino also you can use the same thing. Okay. And now what you can do is, I'll give you an example. So this is what we have seen. Right. So now this is what your microcontroller. Now can you write a program for this? Interface one keyboard to the microcontroller and LCD panel to the microcontroller. The moment the key is pressed, that has to be displayed on the LCD. You can try out this. So this is what simple program, okay, of interfacing LCD to the microcontroller. I hope you understood. Okay, I hope you understood. It is hardware in detail, algorithm, and then the step. So the material which I followed is from Microcontroller by Kenneth J. Ayala, is what you can say, the book, and then these programs are available, and then you can practice it. Is that all right? Okay. So today we have seen the interfacing of analog to digital converter, digital to analog converter, LCD interfacing to 8051 microcontroller. Is that all right? Possible keyboard interfacing is also very important. The same thing you will be doing these days, the mini projects and all for Arduino board. You can check it out. And all these things, they are available in form of functions. So I'll stop today's class. Okay, I hope you understand. This is microcontroller programming. Little bit, you have to get practice. You practice, you will be understanding these things. Okay, all right. And if any supporting boards are available in your college of interfacing of this microcontroller, you practice by writing this simple program. Okay, assembly level program is always better. Okay, all right. So we'll meet in the next. And most of you will be doing LCD interfacing in your Arduino. Okay, in Arduino case you will be doing, right. So then the moment you use Arduino, you can use this program. You can use this program. Arduino, you can connect like this. This is what the program you can write in Arduino. Okay, right. So we'll meet in the next class with like timers programming of onboard timers of 8051 and how